I'm Fraser Torpy, and as the introducer said, I'm the Director of the Plants and Environmental Quality Research Group from Sydney, Australia. I want to talk to you about the challenges in modifying the current systems we're using plants that we use to remove air pollution and trying to get multi-purpose out of those systems and grow food as well. I'd firstly like to acknowledge the traditional owners of the lands from where I'm giving this talk. Firstly, urban air pollution is widely considered to be a large-scale epidemic that's growing. Urban air is known to be polluted. The activities that we do in cities leads to air pollution, and there's no way of avoiding that. We might reduce vehicle emissions, but the surfaces and the materials we use still will produce air pollution in the foreseeable future. Air pollution is particularly problematic indoors, where as well as the outdoor pollution, we have indoor sources, particularly synthetics and cooking and cleaning, that produce really loud, poor air quality, typically 3 to 5 times worse than outdoors. The global disease burden from air pollution has been stable for the last quarter of a century now and is actually increasing in some parts of the world. And this has certainly been recognised by the World Health Organization. So air pollution by removal by plants is reasonably well known now. Certainly governments and industry have recognised the ability of plants to pull down air pollutants, and they've spent significant capital on building large area green spaces explicitly for the purpose of removing air pollution. When we go and assess the effects of these green spaces, we find significant reductions in most of the key air pollutants: particulate matter, the gaseous air pollutants, volatile organics, the hydrocarbons emitted from fossil fuels, and also modern synthetic materials. Of course, we get sequestration of carbon dioxide, particularly in forest-type green spaces. And what this all leads to is detectable health benefits in populations adjacent to significant green space. And of course, green space provides lots of other advantages as well. Passive green space has significant limitations. Plants in their normal state, so indoors potted plants and outdoors forests, have relatively low pollution removal rates per unit area. What that means is that you need a lot of plants to make a significant effect on local air pollution. Secondly, passive removal of particulates is subject to resuspension. So what the plants do is they increase dry deposition or adsorption of the particulate matter, and then when the wind blows or it rains, that particulate matter is resuspended. So it's a temporary removal effect. And finally, the removal of all pollutants is strictly limited by diffusion. For the pollutants to be removed by the plants, the pollutants have to make their way from their source to the active parts of the plant system, which in many cases is substrate bacteria living on the root systems of the plants. So they're problems. So what we do in research, of course, is try and fix things. And one of the directions we've headed in is green walls. Clearly, green walls or vertical greening systems have a dramatically increased planting density per unit area of footprint. So you get a lot more plants in a small amount of space. Secondly, the substrate in vertical greening systems as well is much more exposed to the atmosphere than in traditional planting systems, meaning the pollutants have more access to the microorganisms growing in the substrate and as a result, removed much more efficiently. And best of all for vertical greening systems is their flexibility. They can be easily fit into modern urban systems. They don't take up much space and they can be modified to fit all sorts of different spaces like urban canyons. Of course, as scientists and engineers, we try and improve on nature, and we've spent the last decade or so trying to make these systems more effective. So we know we can improve the pollution removal efficiency of plants. For example, if we make sure our plants get the right light levels for that individual species we're using, they'll be healthier and they'll remove pollutants more effectively, particularly carbon dioxide. Secondly, we know that plants remove pollutants at different rates. So if we choose the most effective plants for the given air pollutant profile in a location, we can get better results. Modifying the substrate to encourage the bacteria to remove the pollutants, once again in a specific area, also bears dividends. And hydroculture is also useful, particularly for carbon dioxide removal. The biggest update, however, we've found in the last 10 years of research is the activation of plant-based systems. So you remember I said a moment ago that pollution removal rates are limited by diffusion. To remove that effect, what we do is we use low voltage mechanical fans to increase the rate of airflow from the polluted source through the substrate, through the plant foliage and back to ambient. This is the real magnifier of plant effects. So when we use these systems, we get dramatically increased pollutant removal. The picture shows one of the earlier systems we tested from a Finnish company called Naturevention, and it was really effective at removing pollutants, a lot more effective than traditional systems. And now, given the large effect sizes we've got out of these botanical biofilters, we're now testing them outdoors. There's a trial we did several years ago with an active green wall system on a freeway in Sydney. And what we found was significant clean air delivery rates for all of the major typical pollutants that would be generated from freeways. The effect sizes are good. They're better than most of any of the mechanical systems available at the infrastructure level. And once again, governments paid attention to our results, and we're now seeing these infrastructure scale systems being built. This is a freeway in Brisbane, in Queensland. It's going to have active green walls each side of the freeway. The car park here was explicitly built to act as a pollutant sink, not a source. A multi-storey car park is usually a source of pollution. In this case, it is actually a sink for pollutants. Now, altering these systems for food production is going to face one major challenge, and that's going to be contamination. It's well known that contamination is of major concern for urban farming across the board. And of course, the systems designed for air quality remediation will naturally accumulate the pollutants, both from stormwater and particularly from air, at faster rates. And those pollutants will be taken up through both the roots and the plants and the leaves of the plants. As I said before, most organic pollutants are degraded by the bacteria in the substrate and also on the leaves. But of course, heavy metals can't be biodegraded. And there are a large range of heavy metals that are problematic in urban environments. Of course, as well known, heavy metals have significant effects on human health. Interestingly, plants won't be affected health-wise because plants grown both as crops and also in vertical greening systems, for example, aren't used for very long. Their life expectancies are only a few years at most, so they won't have time to be affected significantly by these metals. Of course, when urban crops are being tested, high metal loads are really common and certainly in excess of safe levels. I'd like to suggest and propose that all food plants accumulate metals. Reading the literature, there's plenty of papers that say one plant takes up more metals than another, but looking at the effect sizes, the rates at which different root and leaf crops take up pollutants, they're all within an order of magnitude. So we could confidently say all plants accumulate metals. What is interesting is that the spatial variation, when metals are tested in plants, across small spatial scales, we get significant variation. The general conclusion from the literature is that most crops are considered safe, but is safe good enough when there is regular high levels of metals found in crops, particularly those grown in urban areas? So how are we going to try and modify our air cleaning systems? Substrate rotation is a component of air pollution removal phytosystems. It's very effective. It does remove, of course, the pollutants from the system and would allow food growth in those systems, but the problem of those pollutants is moved elsewhere. Phytoextraction is a technology that needs to be further examined. If we co-plant food growing air pollution removing systems with accumulators such as this center, we might find good results. These plants accumulate metals at a much faster rate than our food crops, and they may mitigate those metal levels down to safe. Soil amendments, there are a range being proposed. The big one's going to be maintaining a high pH. A high pH reduces the bioavailability of metals and makes them much safer. And of course, wash your crops before you eat them. Plants grown in urban areas exposed to air pollution need to be washed. So can we use these functional air pollution removing green systems for food production? To some degree, the goals of the two systems conflict. One is to accumulate air pollutants, the other is to, of course, avoid them. I believe that combining the systems is feasible, but we're going to need a lot more research, particularly for these high accumulating active systems. Site-specific field trials will be required in any location where significant food crops are going to be grown. The mitigation methods are insufficiently studied for systems with high air pollution accumulation rates. And I would also personally like to see some research done on staple crops. Most of the urban farms that we see grow high value crops like herbs and expensive fruits and things like that. How about trying to feed the world and growing some staples, some starch crops and so on? Thank you. I'm not used to speaking for 10 minutes. I hope I communicated the message that I was trying to get across. Thank you again for having me.